have Steve Gehrke talking about the spatial temporal measure of land use mix. And in the second half, we're going to have Kihong. So we're going to break it into two parts. So after Steve's presentation, we're going to have time for questions, and then Kihong is going to go after. And don't forget to sign up. You can pass that. It's not updated, so don't worry if you don't see that your attendance is up to date. Thank you.
This presentation is toward a spatial temporal measure of land use mix. It's some work that I presented at TRB, and it's a synthesis sort of my dissertation proposal, so you get a 15-minute snippet sort of the ideas that I'll be going forward. So I'd like to note my co-author and also my advisor, Dr. Kelly Clifton, who helped sort of with some of this work. Okay, so an overview of sort of the presentation before I delve into it is that I'm just going to give some background, which will include the research context, the motivation behind this sort of research and looking at land use mix and active travel. And then I divide this concept of land use mix into 3 different elements, and I'll go through each of those elements and talk a little bit about them. Then I'll provide some discussion on the strategies that have been provided in the literature representing these different elements of land use mix, some of the shortcomings, both theoretical and methodological, with representing these, and then finally some conclusion, which I'll synthesize these elements and then provide some implications, perhaps going forward with this research. And so some background. And so I'm sure many of us are familiar with mixed-use development, but a lot of our urban policies, which encourage active travel, reducing auto dependence, and mitigation of peak hour travel, are rooted in growth management strategies. And one of the more popular growth management strategies is this notion of mixed-use development. And so the reason why this is important to travel is that mixed-use developments improve built environment efficiencies and increase local accessibility to out-of-home activity locations. So by bringing functional origins and destinations closer to one another, we're reducing the travel cost of non-automotive modes and make them more competitive with auto transport. There have been a variety of different metrics which have been established to evaluate the effectiveness of mixed-use policies in the relationship to travel. And sort of this began as an interest in the urban planning profession, but it's now moved on more towards the public health field and other fields. And that's because a number of benefits have sort of been cited when we're thinking about increasing the land use mix of an area. And so from a transportation perspective, I've mentioned some of these, but there's shown to be an association between this increased land use mixing and reductions in auto travel, auto ownership, and emissions production. There's also been shown to be induced rideshare and shared parking opportunities and arrangements that can occur from this efficiency in the built environment, a distribution of travel demand across the day and week, and then ultimately these benefits and others lead to the promotion of transit and active travel opportunities. But from a public health perspective, this location of a variety of opportunities in close proximity, which is sort of what this construct represents, in addition to this heightened visible interest in the built environment, so an area like on the left and right here, you kind of see an area which looks more inviting and there's more going on, and so it's supposed to induce more active travel options. And so we know that these in tandem increase the propensity for physical activity, and there's an association of positive implications for physical and mental health in increasing the land use mix in a neighborhood. So the motivation behind this research is that despite these purported benefits, practice still remains guided by limited theory and empirical evidence to substantiate mix as a construct which has an association or a positive impact on active travel behavior. And so I have several objectives pointed out here, but this paper in particular is just focused on the first point, which is to summarize the current approaches to measuring land use mix, identifying the inherent methodological and theoretical limitations within how this has been addressed in the literature, and then proposing a research agenda going forward. And those final 2 points sort of will be my research going further along, which would be to provide both research and practice with an improved theoretical and empirical understanding of the influence of land use mix and active travel behavior, and to also develop a mixed measure which reflects these behavioral relationships that we can then use to inform time-sensitive transportation land use policies, so more innovative policies in transport. So given that motivation and sort of this mixed reporting of results, and we're looking at the link between land use mixing and travel behavior, this may be, often you'll see it reported as the magnitudes will vary, You'll have different associations, counterintuitive associations, and of the sort. And a lot of this may be because the way we think about representing land use mix. And so I've sort of, for my own thinking, I've divided it into 3 separate elements. And the first of which is this notion of land use interaction. So how do we quantify the complementarity of different activity locations? These activity locations are the proxies for which land uses are being calculated in these mixed constructs. And so we know that a proximity of synergistic activity locations has implications regarding the viability of active travel decisions. The second land use mix element, so with any built environment measure, and land use mix is no exception, we have to select some sort of spatial boundary to measure the extent of its influence, this neighborhood effect. And so the scale element is important in representing a land use mix construct. We know that depending on how you choose the scale to represent the neighborhood effect, it's going to have a varying influence on modeling the determinants of travel. And then finally, which is most germane probably to the study and the contribution probably greatest that will be provided by this research, is this notion of temporal availability. And so this is the opportunity to access activity locations or land use types at a specific time interval or time point. We know that the availability of these locations has consequences for transportation land use forecasts as we go forward. So in thinking about these 3 different elements and just putting it sort of in a rudimentary travel behavior context, is that I'm most focused on this association between built environment and its influence on travel behavior, and particularly land use mix, and so representing it as these 3 different elements. And so now I'll go through what the literature says about each of these 3 different land use mix elements. So the first one, this notion of land use interaction. And so in the literature, I've broken into 3 categories of measures that have been used to represent the quantification of these complementarity of activities or land uses. And the first of which are accessibility measures. And so this is just a distance-based measure looking at, in this exemplar neighborhood, in the upper center half there you have a residence or a residential land use, and it's located a quarter mile network distance from the school located in the lower right corner. You could also think of intensity measures, and so this could be something like walk score, where we just have a count-based representation. And so in this exemplar neighborhood, we just have 1 school. And so just one. It doesn't tell us a lot, but it tells us something about the mixing going on in this neighborhood. And then you could look at perhaps the spatial footprint, so a percent-based measure of land use. So there's just 1 school in this exemplar neighborhood, and so you just have it covering 2.5% of the spatial footprint. And I would argue that we're typically, when we're thinking about land use mix, we're not just looking at either the relationship between 2 different land uses or activity locations, or just the representation of one single one in the unit, but we're thinking about the pattern of these measures. And so this is typically represented through composition measures. And so what's the spatial allocation of different land use types within a spatial extent? And so a common one that is used in literature is this idea of entropy. And so you would have a measure between 0 and 1, and 0 represents the dominance of a single land use type within a neighborhood. A measure of 1 would be an equitable balance of land use types in an area. But borrowing from ecological research, not much thought has been given towards this complementary idea of configuration. And so this is now the spatial arrangement. So there's some synergy that happens when we move around these locations within an area, not just the allocation of them within a neighborhood. So kind of looking at this on a larger schematic, on your y-axis, you have composition complexity, and on your x-axis, you have configuration complexity. And so generally, when we're looking at the lower left corner, you begin here, and this is just the dominance of a single land use type, so there isn't any mixing going on really, and it's large land use parcels. And so usually we're moving up this axis and looking at something more like this when we're talking about the pattern of an area. And so you can see that there's a good allocation of different land use types within that exemplar neighborhood, but something's missing. And if this configuration, if we start to look at this, you can move along the x-axis into that upper right corner, and you sort of get at this idea of these intermittent parcels or something to it that could help explain active travel research that's currently missing from our measures. And so I've then kind of noted a number of the conceptual and methodological concerns aside from this that I've also found and through this review of the literature. And so the first point is this limited consideration towards the functional complementarity of land use types. So often when people are measuring land use mix as a pattern measure, we're just looking at the heterogeneity of different land use types, but we're not really thinking about how do these different land use types interact with one another? You may not make sense to include an industrial land use type in this sort of area if you're looking at land use mixing of a neighborhood. The ideal level of mixing is often represented as entropy measures, so you're looking at these equal distribution of land use types, and there's no strong theoretical support for doing this, aside from a regional idea of jobs housing balance. But if you start to look at more land use types, it starts to fall apart, that idea of equal balance. Also in the literature, there's been insufficient attempts to link land use types with the primary trip tour purpose. And so this is this idea, again, if you're looking at recreational travel, why would you include an industrial land use type within this mix of a neighborhood? Methodologically, the data are given to us in a certain way, so there are a variety of different typologies. How do we define land use categories? And that impacts our analyses. The absence of the spatial configuration has been noted. I think it's an improvement to include that in future land use interaction measures. And then often we look at the trip segment rather than tour level. And so by looking at just the trip segment, we don't necessarily get at the full reason or full demand for this travel in the first place. And so that's sort of going over the land use interaction element. The second element is the geographic scale. So once again, how do we spatially bound these measures of land use interaction or land use mixing? And the literature has divided into three different strategies. And so the first of which is this idea of fixed scales. And so these, as this picture shows you here, can be administrative. So thinking about cities or counties, some administrative authority is what the boundaries that we look at for this phenomenon. Statistical, and so these are census-based delineations of territories, and so often we're looking at these because the data are available and it's convenient. And are artificial, and so you could cast a fishnet across the study area and look at what this land use mixing look like in a particular grid cell. So there are a number of inherent flaws, and these have been documented pretty well in the literature. So now individuals or researchers are moving more towards a sliding scale representation. And so these are aerial buffers where now you have the land use in the center or the activity location in the center, and you look at the neighborhood effects surrounding that. And so you don't just have this residence which is pinned in the corner, which could be more impacted by this scale than over here. Network buffer, so we can include some sort of impedance factor, whether it's the street network to representing this, or activity spaces if we're starting to look at multiple activity locations, not just one particular location. And then a third type of category is perceptive scales. And so this borrows from the work of Kevin Lynch. And so this is looking at cognitive and mental mapping as ways to measure the influence of the neighborhood or the built environment within a certain neighborhood. And so those are three ways that scale has been represented in the literature. Some concerns with this that I've noted when we're thinking about linking land use mixing with active travel behavior is that often it's a single operationalization strategy that's selected for all travel modes. But if we're thinking about the travel times associated with these mode selections and auto use or car use, you may look at different extents because you can only reach so many opportunities in a given amount of time. And so that should be thought about when we're looking at specific modes and representing land use mix. A single spatial extent could be selected for all travel purposes. And so if we're thinking about discretionary travel, these trips could be more elastic. And so individuals may travel a farther distance to complete these. So it's important to look at the larger neighborhood effect when you're thinking of that versus maybe a mandatory travel trip. Methodologically, there are a number of concerns. The first of which would be the measuring of mix at a single trip end for all travel purposes. I talked about the tour-based sort of analysis. Insufficient attention to mix at both a local and regional scale. So mix can happen to different magnitudes or different extents at different scales simultaneously. And so to kind of get at ideas of spatial autocorrelation and stuff like this, it's important to measure them at both extents. When we're thinking about impedance factor for sliding scales, it's almost unanimously going to be looking at the street network. But you could think about including topography or travel time or other things to calculate this impedance of reaching areas when you're calculating these buffers. And the last 2 points, I'm not going to go into here for sake of time, but they borrow from geography literature and this notion of the modifiable aerial unit problem and the uncertain geographic context problem hampering our investigations of this mix. So that's sort of a review of the first two elements. The final one is this idea of the temporal availability. And so this borrows from the subdiscipline of time geography where you have this constraint-based approach to looking at the influence of the built environment on travel behaviors. And so typically when we're looking at land use mixing, we're doing it with a static snapshot that doesn't account for any variation in time across the day. And so we have this neighborhood level, which you guys are familiar with at this point, and we look at just a static snapshot of what does the mixing look like that. Or we have that school, so at a site level, we can think about what does land use mixing look like. But we know that in the morning, there's a different feel going on. So from midnight to 6 a.m., all the activities are closed, so an individual doesn't really have the opportunity to go out and participate in any of these. They're kind of confined to their own residence. So using just an old entropy measure, this has a different feel or a different measurement. And one of those activity locations at the site is the school, and that's closed. And then, once again, if you move throughout the day, so the middle half of the day, from 6 a.m. to 6 p.m., you see now that perhaps these residential opportunities, individuals are out, so these aren't, but all these activity locations have now been activated, and so now individuals are conducting activities, and so the land use mixing of this neighborhood looks a lot different than it did in the morning, and definitely different than a static snapshot. And the school is one of those locations which has been activated. And finally, now you move towards the evening, and you have where some residences are now occupied again, and some of the activity locations remain open, others have closed. And so once again, as you look through these three different intervals with just this hypothetical neighborhood, you can see that land use mixing varies across the day. And this opens up an opportunity of using these spatial temporal land use mix measures of looking at, well, this site level, which was a school, could perhaps now become a community center, but our measures now don't really have a good way of representing that. And so there's an opportunity to looking at site level mixing if you start to include this temporal element. So how do you represent time? So within our land use mix measures. And so this hasn't been done, but it's been thought about a little bit when we're thinking about accessibility. And so the straightforward way is that the known temporal availability. So what are the stated opening hours at which activity locations may be accessed? So if something's open from 9 a.m. to 5 p.m., you just mark it, and that's what the availability is. However, these data are very hard to come by, and so there's a reason probably why this hasn't been looked at a little bit more. A second way that we could represent this is just an assumed availability. And so we just fix the assignment of opening hours for all activity locations of a similar regime. So if we have an industrial land use type, we just say it's available from that 6 a.m. to 6 p.m. And we just, across the board, all industry locations are given that time. Or we could do an activity-related temporal availability. So now we impute the assignment of opening hours based on the revealed activity participation that we have in some travel survey diary. And so we can now get a probability or a distribution of different land use types that are open, or what time they may be opened based upon this. And so these are three ways going forward that we can think about representing this temporal element within our land use mix measures. And so just some concluding thoughts. Here's sort of the big picture, the overview of these different elements, the different strategies for representing them, and then as you move left to right, sort of this increased complexity in operationalizing each of them. And so for my dissertation, or going forward, I'm looking empirically at these. And so stay tuned next year, so maybe I can come back here and tell you what the results are. And then what are the research implications for this? So obviously, it's to guide policy. So at Metro, there's this need or this discussion of an activity spectrum. So we have these neighborhoods that could be 14-hour, 18-hour, 24-hour neighborhoods. But there isn't really yet a strong empirical measure to define what these neighborhoods should look like. And so doing this sort of research would help inform these policies. Identifying travel outcomes that are anticipated for new mixed use and neighborhood infill projects is a potential implication of this research. So this doesn't get the time piece necessarily, but it does get at the interaction and scale elements. And then another point is to guide other innovative policies. So downtown activity and business retention. So we know that traditionally our CBDs and areas have sort of everyone after the workday leaves these areas, but understanding this temporal dynamic nature of land uses, we can kind of start to inform maybe policies that keep businesses and these areas active throughout the day. The liberalization of opening hours could be looked at as a way to increase the land use mixing across a particular day. Multi-purpose shared spaces, so that's an example I showed you of the school becoming a community center in the evening. And then more traditional things such as shared parking arrangements can be looked at with this sort of measure. And then of interest to me is this providing travel demand modeling with the research with a spatial temporal land use mix measure. So the temporal aspect is currently missing, and this could be achieved towards just simply linking activity opening hours to land use availability when we're specifying our pattern measures, so looking at that composition and configuration measures. And as of now, these temporally static measures likely underestimate or overestimate the extent of land use mixing in an area, so there's sort of shown this importance perhaps of representing time within these measures. Just finally, I have done some preliminary research on this, and this paper, this research is now forthcoming in the Journal of Transport and Land Use. So if you would like a copy of it or talk more about it, you could email me. But thank you. I appreciate your time. Questions?
You mentioned in terms of the temporal land use mixes, how a school could become a community center, for example.
Sure.
Are there any good examples, either in the U.S. or elsewhere, where that's very prevalent, not just with schools, but any sort of land uses switching based on time of day?
Yeah, I don't know that's prevalent. I wouldn't say that. I think there are examples. I don't have any anecdotal stuff off the top of my mind. But I think that's an easy one. I mean, you are sort of confined to what the structure is as to what type of land use it can become or what activities could occur in that same structure later in the day or earlier in the day. And I think that you think of a school becoming a community center of individuals. I mean, you've seen that happen, so it's just an example that maybe I could point to. But I don't know nationally. I just think it's a good way of, instead of just looking at the mixing in the neighborhood level, we could look at the site, and there could be gained efficiencies just within buildings. So thinking about how we could look at land use mixing or activity mixing within these locations. So, I don't think there's a lot of adoption of those ideas quite yet. Alice?
So are you primarily interested in investigating the different measures of relationships with observed travel behavior, or are you also thinking about things like something kind of a step back from what we're actually doing with how they're thinking about things? Or are you also trying to them based on what people stated preference, maybe not stated preference, but like surveys of how are people thinking about neighborhoods?
And so for this proposed research, I'm specifically looking at just the Oregon Household Activity Survey and applying it to revealed behaviors on that. If there were funding available, there'd be interest in more current surveys to conduct looking into this. But I do think that this is just an application within transportation, but I think the idea of land use mixing, can be just removed from that travel connection. And so, I do think there's a lot of opportunities for using it elsewhere.
Are you looking at the link between these measures of land use and like total transportation and like mode choice?
Yeah. So I would be, and so one of them. So this kind of gets back at Alex too. I could look at like destination choice, but so mode choice is what I've proposed to do on one of them, and so that kind of gets at the scale question too of thinking about So if you're looking at the land use mixing of a smaller neighborhood, you're trying to invite more pedestrian travel, and maybe transit use, and so connecting it to mode choice, but you get any sort of travel outcome. I think this could be connected to trip generation.
For your measurement of access, you're looking at distance to destinations. I was curious if you're looking at all at the time it takes for crossing streets, if you're including crossings or street intersections into that measure of network distance or effective network distance.
So I think the example I showed of how we classify accessible or different land use interaction measures, I pointed to that accessibility as just being a distance-based measure. But when I'm looking at quantifying land use mixing, I'm going to use those pattern measures, and so the composition and configuration. And so that comes either towards the spatial arrangement of land uses or the spatial allocation. And so I'm not specifically looking at accessibility measures. I'm more looking at the supply side of it. But I think that's sort of the short answer to that.
Are you thinking about the impact of land use mix on property values?
I haven't. Not looking at that as an outcome in this particular study, but I think that is interesting. I mean, you see there's a demand for individuals to kind of reside in these areas where you have this local accessibility, and so I think that if that demand's not met, there would increase your property values perhaps. So I'm not particularly looking at that, but I think it's an area.
I'm not sure if you have applied this to specific be replaced, or just thinking about what kind of data would be used, and also if the data available right now would be a constraint in terms of applying all these concepts like you described.
Yeah, it is. So the land use data are available for the same time that the travel data are available. But then getting the opening hours, you can kind of scrape off Google's website and kind of get when those are occurring for different establishments. But then that would be the present, and assuming that, 2011, when this data were collected, that those establishments were all there. So I think that's the tougher one to do. It's the known temporal availability. And so you could probably look a little bit more at just get a distribution of what a certain activity's opening hours are and apply those to land uses. Or the assumed temporal availability. It's pretty easy to say a commercial area from 6 a.m. to 6 p.m. But yeah, those data are pretty hard to come by. And I think that's why it hasn't been looked into quite a bit yet.
Thank you very much. Thanks.
Hello everyone, my name is Kihong Kim. I'm a PhD candidate in Urban Studies and Planning here at PSU. Today I'm going to talk about imputing missing data for land use and transportation models. To handle missing data, this study will introduce multiple imputation by chained equations, so-called MICE approach, based on recursive partitioning. This is a part of a research project called Continuous Data Warehouse for Land Use and Transportation Modeling and Planning, led by Professor Liming Wang. Okay, I'm going to start with motivation. Today, land use and transportation models move from macro to micro in terms of spatial unit of analysis. You can easily imagine the advantages of micro-level geography. For example, parcels are behaviorally meaningful. For land use model, we observe actual transaction, regulation, and development at the parcel level. For transportation model, we can represent people's activity locations on parcel so that we can incorporate parking and work access into the models. However, missing data are a common problem, especially for micro-level models. Professor Waddell, who invented urban SIM, said 70% of efforts in land use and transportation modelings are about the data cleaning, including handling missing data. There are some ways of handling missing data. We can manually inspect and clean, or we can use a set of rules to fill in missing values. Also, we can develop classical statistical models or machine learning techniques, machine learning models. However, this current approach is essentially single imputation. In other words, we replace a missing value by only a single best guess. So we ignore the inherent uncertainty of missing values. Based on this motivation, we introduced multiple imputation proposed by Rubin in 1987 as a flexible way of handling multivariate missing variable. We apply MICE approach. We also explore different types of imputation model embedded in MICE to capture complex interaction effects with minimal efforts of model specification. So let me explain some backgrounds about this methodology. So we have incomplete data in which we have one single missing variable. First step is to generate multiple imputation data set by building an imputer, and then we replace missing value with random draw from the predictive distribution of imputer. Second step, we analyze M imputed data sets separately but identically by developing, for example, linear regression to produce M estimates. And then step 3, we combine M estimates using Rubin's rule. I'm not going to go detail about Rubin's rule, but basically we use Rubin's rule consists of simple arithmetic calculations to compute the overall mean and the overall variance. Next is about mice. In a large data set, missing values, we often observe missing values in more than one variable with arbitrary pattern. We have two general approaches to handle multivariate missing patterns, joint modeling and mice. In joint modeling, we assume multivariate normal distribution of all variable in data sets. Whereas mice, also known as fully conditional specification, assume a series of conditional distribution, one for each missing variable. Mice becomes popular due to the flexibility, meaning that we impute each missing variable based on its own imputation model. Let's move on to mice algorithm. I'm not going to go details for this algorithm, but basically we fill in every missing variable in the first, and then we impute first missing variable, and then based on imputed value, we impute second missing variable. And we repeat this process for all missing variable. And then to stabilize, we repeat these steps. And then we produce multiple imputed data sets. Let's move on mice with recursive partitioning technique. Success of mice really depends on how well we specify imputation model for each variable, each missing variable. However, in practice, it is not easy to build the imputation models because many missing variables may have complex distribution, so that we cannot, parametric statistical model do not work very well. Also, there may exist interaction effects among variable that is hard to find out. To mitigate these challenges, we apply recursive partitioning techniques. One of the most famous recursive partitioning techniques is classification and regression tree called cart, in which we build a single tree. For the purpose of mice, we don't need pruning procedure. Another famous recursive partitioning technique is random forest, in which we generate multiple trees. by bootstrapping and random variable selection, and then we average multiple trees. Based on this methodological background, we apply mice with recursive partitioning to parcel data. Case study area is Multnomah County in Oregon. We obtain the data from Metro Regional Land Information System. We have about 270,000 parcels. In the fourth quarter of year 2011, we found about 16% of parcels are missing, at least for one of building floor area, building value, land value, and land use type. We use R, mice package in R for for imputation, multiple imputation. As a first step of mice, we choose several predictors. This table shows predictors that we use. First for missing variable, continuous missing variable, we scale down for easier interpretation, including FAR, building floor area ratio, which is building floor area divided by parcel area, which is semi-continuous. We have 7.5% missing values. Also, we scale down building value by dividing by parcel area. BBPA is semi-continuous. Semi-continuous means we have a lot of zero values in this variable. We found we have 1.2% missing values in this variable. Also, we scale down land value by dividing by parcel area, which is also continuous, semi-continuous, and we have 14% missing values. Also, we have 9 land use type categorical missing variable. For better prediction, we added non-missing variables as well, including 2 parcel attributes, such as parcel area in square feet and 10 districts for planning analysis. Also, we added 2 neighborhood characteristics, such as year 2010 number of population and at the census block level, census block group level. Also, we add year 2011 number of jobs at the census block group level. Okay. We found this set of predictors are characterized by a mix of continuous and categorical variable. Also, missing variables are continuous but severely inflated with zeros. Also, we thought there are lots of interaction. We thought lots of interaction effects may exist. So initially, we considered 3 competing imputation model, including predictive mean matching and 2 recursive partitioning techniques like cont and random forest. For predictive mean matching, we simply sample from the distribution of observed values. And then we decide number of imputed data set is 5. So to To evaluate the predictive accuracy of the three competing imputers, we create validation data set in which there is no missing values. For each missing variable, we make 5% of values to be random at missing at random. And then we run each of three competing mice models. Then for each missing variable and each imputed data set, we compute R-square value to compare original value and imputed value. So this table shows assessment results. First column is types of imputation model. Second column is missing variable, including FAR, building value per parcel area, land value per parcel area, and land use type. Third column is validation measure. We use RMSE and R-square value for continuous variable. We use accuracy rate for categorical variable. And from 4th to 9 columns, you can see each of multiple imputed data sets. And then last column, you can see average value of validation measures. Overall, recursive partitioning technique performs better than PMM-based mice. Then, between cart and random forest, we found FAR and BBPA performs better than random forest. For LBPA and land use type, random forest-based mice performs better than cart-based mice. But random forest is computationally random forest mice has computational burden, so we decide under the limited computing power, we decided cart-based mice performs the best. With this assessment result, we now run the cart-based mice for the original parcel data set with missing values. Since we do not actually observe the missing values, we cannot quantify the imputation performance. As a simple way, we show a graph. We show the plausibility of the imputation in this graph. Red dots are imputed value. Blue dots is observed value. And then this first panel is about FAR imputation. Second panel is about building value per building area imputation. Third panel is about land value per parcel area imputation. There are some room in this study for future works. As you might notice, we only generate multiple imputed data sets. Actually, we didn't conduct second and third steps of Rubin's multiple imputation. So we need to fully apply Rubin's multiple imputation by developing hedonic regression model on building value to see if uncertainty is embedded in regression coefficients estimates and significant tests. theoretically, random forest performs better than cart. So we need to improve the performance of random forest-based mice by increasing the number of trees with more, based on more computing power. Also, we can consider other machine learning techniques, such as supporting vector machine and Bayesian network for the purpose of benchmarking. You can see this study in this paper. I acknowledge Professor Liming Wang. He gave me motivation for this study. Also, he gave me extensive methodological insight. Thank you for listening. Any questions?
How easy would it be to expand it from Multnomah County to more counties?
Actually, we tried to impute all parcels in Portland metropolitan area, but it never ended. So we chose only Multnomah County.
I don't know if I followed it carefully, or fully, but have you counted? Does your work account for the idea that the missing variables or the missing data in your data set might not be kind of randomly caused? So in other words, there may be some kind of systematic trend which leads for some parcels not to have certain variables and some parcels not. I mean, there are statistical techniques for trying to taking into account that likelihood of having missing data and in the presence of unobserved characteristics for the variables. It's been a while since I looked at this, but it's the Heckman techniques for trying to uncover those missing variables.
Yeah, that's a great question. Actually, in this paper, we assume missing and random, but there is other technique to handle not missing and not random. So maybe in the future, we're gonna try to develop imputation model based on not missing and random. Yeah.
So I was thinking, what part of Portland did you had complete? You had some sample of data that was complete that you used for, to get this application. But I was also thinking, like, if you could mention where the data came from, what area, but also how do you take into account there could be different areas that have very different amount of variability in each one of the variables that you're trying to estimate. So is there any rule of thumb or any kind of guidance in terms of what methods should be used when you have very high variability versus very low variability?
Yeah. We found some parcel in downtown area. Some parcel in downtown area has a lot of missing value for building square feet, because I heard Metro has building square feet value from LiDAR data. So LiDAR detection cannot capture buildings, closed building. So that is not missing and random. So we have to improve those kind of non-missing at random values. Yeah.
In this case, Dave, we use the whole monoma technique, so it's all the parcels. The first part of the so-called assessment is because we never actually observe so-called missing values still missing. So we kind of artificially generate some missing values to give us a sense of how good each of those algorithms performs. And then the final part is to actually apply the card to actually impute those values there, which are missing. The attractiveness, why mice, particularly card and some other emerging learning technique is attractive is because supposedly it should actually handle each of those cases like Miguel just mentioned, whether you have a certain value, a certain variable has a very high variation or some other variable has very low, or there are maybe some spatial variation for those variants across different variables. Supposedly that can be handled by the so-called partitioning of variables to data set how each of those variables interact with each other. We include the district variable as one of the element or imputers, so that variable will control or automatically used as a way to partition those data sets into areas with more homogeneous only or homogeneous less variance for one subtopic variable. So supposedly it should be pretty robust algorithm, but then the computation is definitely one bottleneck at this point. It takes a rather long time to run, especially for random forests. So at this point we haven't been able to run the 4-county equivalent metropolitan area all at once. Ideally, that's what we want to do. But the computation and memory is a huge bottleneck.
If I understood it right, some of the tests that you did with the applied data set was sort of measuring the precision of these methods and whether you can improve the precision of the estimates but not the accuracy. Have you considered like purposely removing data, purposely creating missing data so that you can compare the accuracy of these methods?
Yeah, that is next step actually. So to fully apply Rubin's multiple imputation, we need to develop regression model, and then we combine multiple estimates, and then we can compare those regression results versus list-wise deletion regression model, so that we can see if uncertainty is embedded in regression model using imputed values. Yeah. Thank you.
Next week we have another round and final week of TRB presentations. Thank you.